Daniele Vanerio. I'm an executive PhD student at Polytechnic of Milan, and I'm the mechanical engineering R&D manager in Caracol, which is a company which operates in the field of large format additive manufacturing, and in particular with FGF, so fused granulate fabrication technology. What is FGF? This is a bit slow, but yeah, we have basically a robotic arm with an extruder, single screw extruder as an effector. Doesn't start. Anyways, basically we have, yeah, the movement is given by the 6-axis arc. Then the single screw extruder is able of processing polymers, so thermoplastics and thermoplastic composites, so polymer matrix with glass fiber or carbon fiber inside. The objective of this study is to face some of the open challenges for this technology, which are the improvement of the dimensional accuracy and, even more important, the reduction of the interbit porosity and the increase in layer bonding, so avoid poor layer bonding. In the image, you see some typical interlayer porosity. So one of the main causes of all of these issues is the imprecise prediction of the bit width. Hence, the aim of this study is to develop a model which is able of precisely predict the width of the single bit. Here below you see a small animation. So at first we have the 2 bits with a gap inside. This would create interbit porosity. If we make them closer, also the animation has some problems. So if we make them closer, we first have an optimal condition in which they are superimposed with no excess material. And then if they get too close, we have some excess material, which translates into poor quality of the printing and even failure, or in some cases, other type of interbit porosity. So we started from the state of the art. We noticed that there's a lack in studies regarding the bit with prediction for FGF technology. And while there are some studies regarding this topic in FDM, and FDM shares many similarities, many characteristics with FGF. So we ask ourselves, if could FDM models be adapted to FGF? And we selected Wang et al. Model, which was then used as a baseline for the development of our model, of the model presented in the slides. We can start with the parameter definition. So we have this simple geometrical formula for the width. The geometry is basically a rectangle with 2 semicircles at the extremities. In the formula, you see the bit width, the layer height, and the bit cross section. The bit cross-section can be calculated as the ratio between the volumetric throughput and the transverse speed, in this case, of the robot. It can be also calculated as the product of the width for the height for a correction factor, which is a factor which corrects according to the semicircular shape at the extremities. From this, we can we pass to the instrumental setup. The setup is, as I said, a robotic arm with an extruder at the end. And we extruded, we chose as a material for the experiment, ABS with 30% glass fiber, because it is like a commodity material we use very often for many applications. This is the design of experiments. We started by investigating the throughput and low regulating the throughput. We analyzed 10 different levels. For each level, we have 6 repetitions in measurement of the throughput. For each of these repetitions, the extruder and the robot were in a fixed position, so it was not a printing condition. Then, for the model validation, we have some parameters which we varied with 3 levels. These parameters are the volumetric throughput, the travel speed as defined before, and the layer height. We made all the possible combinations, reaching 27 different combinations. For each combination, we performed 10 different measurements, so we reach a total of 270 measurements. The model let's say, the printing model is the one in the picture. So for all tests, the same geometry was printed. It was just 3 different tests. And the different colored area show you the different transfer speed of the robot. So the light blue is 40 millimeters per second, black one is 50, and the gray white one is 60. From this, we went to the image analysis. We used a classical optical microscope. We first calculated the total cross-section of the sample, and then we calculated the cross-section of the single bead by dividing simply the total cross-section by the number of layers. And then we took 10 measurements for each sample for the width of each single bead. So first results for the experimental phase are the ones regarding the throughput. We obtained a pretty good law, pretty simple. We decided to clearly do a linear regression with 0 intercept, because naturally when we have null screw speed, we also have 0 throughput. We found a p-value of 0 and an R-squared value of 99.19. So we consider this law basically validated. Then we go to the most tricky part, so the model validation, geometrical model validation. We decided to show the results as follows. So we have 3 different box plots. Each box plot has a different screw speed. And on the x-axis, we see the robot speed and the layer height. What we see is that we have a good trend, so a decreasing trend for the increase in layer height, which is what we expected. The same can be noticed for the decrease in width when we have an increase in robot speed. And we have just one value for this data set, which lies out of what we expected, which is the one in the case of 60 millimeters per second, 1.25 millimeters layer height. But this is a very extreme condition, is a limit condition for the manufacturing. So this could be the cause. Nevertheless, we have the model data, which are the red ones, which always underestimate the experimental data. Same is true also for the other screw speeds. In this case, you see 8 RPM, so we have an increase as expected in the average width, but still an underestimation. And same is also for the screw speed of 9 RPM. In this case, we can also notice that the first value, so 40 millimeters per second robot speed and 0.75 millimeters layer height, appears to be much wider. I mean, the box is much wider, wider than the others. And this is because this is also a limit condition in which the process is not completely stable, because we have too much material for the speed of the robot and for the layer height. After this, we considered the geometry itself, and we checked if the correction factor was actually correct also in our cases. So we should have h divided by 2 as length of this circular part, but we noticed that in our case, the arc is never a semicircle, is always smaller. So we always have a value of this length, which is below h divided by half. So to conclude, we first of all obtained a model and validated a model for the throughput law. Then we analyzed the effect of the process parameters on the bit width, which were as expected, and we identified the geometrical model for FDM, which can be adapted to FGF, but at the moment we have an underestimation of throughput value, or we have something in the geometrical model, which is the other option, which makes basically the expected width smaller than the experimental one. So in this case, we have to find a more appropriate correction factor, because the ones for FDM was proven not to be suitable for FGF. As next steps, we will first of all develop a model for the throughput prediction also in printing conditions. So not with fixed extruders, but while we print. We will also develop and adjust the geometrical model with basically a new geometry and a new correction factor. Once we have validated a new law, we will integrate this law into our slicing software, which will be able to automatically generate optimal toolpath with bearing width and bearing manufacturing parameters. And last, we will analyze the effect of these process parameters on the main mechanical properties of the material. Thank you for your attention.
Thank you, Dr. Vanerio. Is there any question from the audience? I will ask you to highlight a bit better which are the main advantages of this technique with respect to the fusion deposition modeling.
It's mainly a matter of throughput. So with FDM, you can reach up to 1 kilo per hour.
Mm-hmm.
With this technology, you can go higher than 100 kilos per hour.
Okay.
Also, you have slightly better mechanical properties, and the cost of the machine is much higher. But the cost of the raw material is much lower, because in FDM, you start with a filament, and it's expensive to produce the filament. So you can have, like for simple materials, 20 euros per kilo, 30 euros per kilo. With this amount of money, you can easily buy like PEI with carbon fiber in the form of granules of pellets.
Okay. Thank you a lot for your clarification.